All right, so let's talk about the practice exam. The first one, I guess you've done that in the homework as well, right? It's like giving you a non-convex constraint. You want to derive the convex relaxation of this constraint. Usually the idea for solving this problem is that you first refactor into univariate functions, since you know the convex and concave envelope of each of these univariate functions. You convexify them separately, right? So first, let's do the refactorization, right? Or just call it factorization. Okay. So here, as you can see, there is like a fractional term here. We don't want to deal with that, so you can multiply x1 to the right-hand side, right? Since x1 is strictly greater than 0, it's between 1 and 2. So you can just rewrite this as exponential of square root of x2 plus log of x1. That's 1 raised to the power of third. So now let's introduce some variables such that we can represent as univariate functions. So maybe on the right-hand side, let's write, let's say y1 as x1 raised to the power of third. Right? Then we get rid of the right-hand side. And then for the left-hand side, you can write, maybe introduce y2 equals to square root of x2. And then, let's say, y3 is log of x1. Yeah, and then you can introduce one more variable saying y4 is y2 plus y3. Right, and then y5 is just exponential of y4. Right. And then the constraint will become, y5 less than or equal to y1. Right? That's just the factorization. Did you guys solve it? Some of you guys may have solved it, right? Did I do it correctly? If I did it wrong, you can just say I did it wrong. Maybe I made up those problems, but I'm not guaranteed to solve it correctly, right? Yeah. So with that, you have those factorization. All those are univariate functions. We did talk about how to relax those, right? Some of the simple ways of relaxing those, remember the McCormick inequality can relax by linear terms. If you have a convex term, then you already have the convex function itself is a convex underestimator, but the concave overestimator is the secant function, right? So we can give some examples of that. So let's first do the consider this term, right? y1 equals to x1 raised to the power of third. So if x1 is from 1 to 2, this is a convex function, right? You take the second derivative of x1 raised to the power of third, this is a convex function, but this constraint is not a convex constraint. Right? This is a nonlinear constraint. If you have a convex function, so let's say if f of x is convex, then f of x less than or equal to 0 is a convex constraint, right? It describes a convex region. But if you have something like fx equals to 0, this is not a convex constraint. Only linear equalities are convex. If you have a nonlinear equality, this is not a convex. In other words, this is not describing a convex region. Right? May not be convex. Right? So what I'm saying is that if you have y1 equals to x1 raised to the power of third, although this function is convex, this is not describing a convex feasible region in general. Does that make sense? Okay. Yeah. So then in other words, we need to write a convex underestimator and a concave overestimator of this function, right? So if you plot this function, maybe to give you some intuition. Oops. So this is x equals to 0, and we are interested in x1 from 1 to 2, right? So this is something like here in when x1 is from 1 to 2. Let's say this is 1, this is 2, right? So we need to find a convex lower underestimator of this function and a concave overestimator of this function, right? So the underestimator is very trivial since this function is convex, right? So you can have y1 is greater than or equal to x1 raised to the power of third. This is a convex constraint for x1 between 1 and 2, right? So this is the your convex underestimator. Right. Now, how do we come up with a concave overestimator here? Just do a linear interpolation, right? So if x1 is between 1 and 2, then your overestimator is essentially a strict line segment connecting these 2 points, right? Well, I didn't draw it very strict, but here at these 2 points, we are talking about x1 equals to 1, then y equals to, so it's like these 2 points, x1 equals to 1, then y1 equals to 1, right? When x1 equals to 2, y1 equals to 8, right? So now you can draw this line here, and then that is essentially, let me try to calculate real quick. It should be y1 greater than equals to, the slope would be 8 minus 1 divided by 2 minus 1, right? And then times x1. And then when x1 equals to 1, this should be equals to 1. So you have minus 6 here, which is 7 times x1 minus 6. Okay, yeah. No, should be less than or equal to. This is an overestimator. Okay. Yes.
Could you repeat the overestimation?
Yeah, so the overestimator is, since this function is convex, right? Let me draw it a little bit nicer. So since this is a convex function, an overestimator is nothing but you connect these 2 points using a line segment, right? And since you have 2 points, that will uniquely define a linear overestimator, right? So here, I'm not very good at drawing, but so this is like the overestimator. Well, it's not linear here. Yeah, right. So the 2 points will give you the this overestimator. So if you think about this function, I calculate when x1 equals to 1, then y equals to 1, right? When x1 equals to 2, then y1 equals to 8, right? So that's the overestimator you are talking about, yeah.
Why do we need the concave overestimator when our goal is to convexify the problem? I mean, if like the constraint's already convex.
Yeah, so the constraint, when you do the refactorization, you need to relax this equality constraint, right?
Even if the function itself is convex.
Right, so this is not really a convex region, right? This constraint is equivalent to essentially y1 greater than or equal to x1 raised to the power third, y1 less than or equal to x1 raised to the power of third, right? Only this part of the constraint is convex here, right?
Yeah.
Right, and this part of this is like a, let's say, a well, you can think about it, it's like a concave function on the left-hand side, but here it's a convex function on the right-hand side. So this constraint doesn't describe a convex region. That's why you need to relax that, right? Or, I don't know, maybe some of you look confused. So let's think about a very simple example, okay? So if you have y equals to x squared, right? Let's just talk about a convex function in Rn, right? Y equals to x squared. It doesn't describe a convex region. Why is that? Think about the following case, right? So if you have one side of the constraint, y, let's say y greater than or equal to x squared. This is like an epigraph of a convex function, right? But if you have y less than or equal to x squared, it is called a hypergraph of a convex function, right? So it's a region underneath a convex function, which is not a convex region, right? So this region is a convex region, but this region is not a convex region, right? That's why you need to relax the region that is not convex, okay? Yeah. Okay, so essentially this, if you plot this region here, it is, this region here, right? It is clearly not a convex region. So you need to relax this region by, if the range of x is between 1 and -1, you draw a line here to create a convex relaxation, right? And similar here, when you have x1 raised to the power of a third, only one side of this inequality describes a convex region. If it doesn't describe a convex region, you need to get let's say, a concave overestimator, right? Okay, does that make sense? Yeah. And similarly, let's talk about the second function. Okay, I will do one more, then I will skip the rest, okay? So y2 equals to square root x2. This is, the square root of x2 is a concave function, right? So how does it look like? It looks something like this is 0, then this function looks something like that, right? So this is a concave function. Then the overestimator of this function is actually convex, right? But the underestimator is not. You need to come up with a convex relaxation. So similarly, if you write it as two direction, y2 greater than or equal to square root of x2 and y2 less than or equal to. So the second part is convex, right? This constraint is non-convex, right? In other words, the overestimator is a concave function, so this region is convex. But then when the underestimator of this function should also be convex, the way to relax it is the following. You just pick the range of x2 from 0 to 1, and then you draw a straight line. It will underestimate this concave function, right? Okay, so how do you get this straight line? You just calculate the points, right? So this is 0, 0, 1, 1. So this is nothing but, this line is nothing but y2 greater than or equal to x2. So to summarize, the convex and concave envelope are y2 greater than equal to x2, y2 less than equal to square root of x2, right? So this is the convex envelope. This is a concave envelope. Okay, so now these two constraints are both convex constraints, right? They both describe a convex region. This is like the hippograph of a, should you call it hippograph of a concave function. This is the epigraph of a convex function, right? Both of those are convex regions, yes.
When you solve the problem with those relaxed constraints,
Mm-hmm.
that solution isn't guaranteed to be feasible in the original problem, right?
Right, yeah. Yeah, so it's a relaxation of the convex relaxation of the original problem. But then you can use a convex optimization solver to solve it to global optimality, right? To get the global optimality of the original problem, you need to do some branch and bound. Okay, yeah. Okay, so I'm not going to do that for all those constraints here. You can say this is a convex function, then all those are linear function. Should be easy to do. Okay. And then for bilinear terms, you just write out the McCormick. Right? Yeah. So now let's talk about problem number 2. The part A is probably too trivial to write a proof. Yes?
So like the previous question,
Uh-huh.
the envelope was by definition should be tight, should be very tight, right?
Yeah, so
How do you define tight over like, for example, y2 greater than x2, like?
yeah. So this is the by defined tight is that the let's say the convex hull of this region is a convex hull of the original epigraph. Right? So if you consider, let's say, okay, this function square root of y equals to square root of x, and x is from 0 to 1 here, right? So if you just consider x is defined on 0 to 1, what is the epigraph of this function? That will be this region here, right? So what is the convex hull of this non-convex region? It is nothing but this blue, anything above this blue line, right? That's a convex hull of the epigraph. So the epigraph of the, how do you call it? The convex envelope is the same as convex hull of the original epigraph, right? That's what you mean by tightness. We actually define that in our lecture. Okay, yeah. Any other questions here? Yes?
How would you do this for y4, which is equal to y2 plus y3?
Yeah, it's already linear. You don't need
You don't need to do
to convexify anymore. Yeah. Other questions here? Okay. Yeah, here we gave you 2 optimization problems, right? The first one, it has 2 sets of constraints, g of x less than or equal to 0, h of x less than or equal to 0. And the second one is a little bit different. It's like a disjunctive constraint, right? Either g of x is less than or equal to 0 or h of x is less than or equal to 0. So this is almost too trivial to prove here, right? It is very clear that the feasible region of the second constraint is larger. Right? So you can define perhaps 2 sets, which is the first set, let's call it set A, is x such that x satisfy g of x less than or equal to 0. And B is x such that h of x less than or equal to 0, right? So in the first first problem, the feasible region is X belongs to A intersect B, right? So these two constraints have to hold simultaneously. Well, in the second problem, right, so this problem here, the feasible region is X in A union B, right? Because it says either this constraint hold or the other constraint hold. It's like the union of the two sets. And of course, if you have the intersection of two sets, is always a subset of the union of the two sets, right? So the feasible region of problem 2 is larger than the feasible region of problem 1, right? So that means we have Z2, Z1 less than equal. Wait, so we are minimizing, yeah, so, sorry. Z2 should be smaller. Should be Z1 greater than equal to Z2 star. Right, since the first problem is more constrained and we are minimizing. Okay. Any questions here? So now let's go to the second question. I actually talked about this conclusion in class. I don't know if you guys remember that. We talk about this when we talk about convex relaxation, right? If you convexify two sets separately versus you convexify two sets simultaneously, which one is tighter? Okay? So let's rewrite this problem a little bit, okay? So let's define, again, set A as X such that X satisfy G of X less than or equal to 0. We define B as X such that X satisfy the second constraint. So the feasible region of the first problem is essentially X is in the convex hull of A intersect with the convex hull of B. Right? That's a feasible region of the first problem. Okay. Any questions here? So now what is the feasible region of the second problem? It is X is in the convex hull of A intersect B, right? So you first intersect these two constraints, and then you convexify these two constraints, right? So kind of we are changing the sequence of doing convexification and intersection. Right? The first one is that you convexify two functions separately. Right? If you think about deriving convex relaxation, it's like you have a bunch of constraints, you are convexifying two sets of constraints separately. And the second case is much harder, it's like you consider all the constraints simultaneously, and then you get a convex hull. Okay. As people see the difference of these two problems, right? So geometrically, you probably remember this figure we draw. Let's say we try to draw this again. Okay, so I didn't draw it very well. So let's say P1 and P2 are two non-convex sets, right? So if you consider the convex hull of P1 intersect P2, what do we get? Yeah, it's an empty set, right? Because P1 intersect with P2 is an empty set. So what about the convex hull of P1 intersect with the convex hull of P2? Yeah, it's clearly non-empty here, right? So that would be, you have to draw the convex hull of P2, and itself has a non-empty intersection with P1. Right? So that gives you the geometric intuition that if you convexify the intersection of two sets, that should give you a tighter relaxation. Actually, that's a key in deriving convex relaxation. Right? So remember what we told you in the first question. You are essentially convexifying all the sets separately. Right? So this convex relaxation is actually very weak. So all the research in global optimization, maybe not all the research, but a huge chunk of research in global optimization goes to, if I give you multiple constraints, how do you convexify them simultaneously? It's much harder than convexifying them separately. Okay, so this will give you a intuition of doing that. All right. So here's the intuition, but to write a proof, you cannot draw a picture and then say this is true. Okay. So how do we prove that? One of the ways you can think about this is that we want to show that the second set is contained in the first set, right? So in other words, if you take any point, or maybe when you try to prove something, you can write the goal of your proof, right? So what you want to do is that take any arbitrary point, let's call it maybe x hat, that is in the convex hull of A intersect B. Then you want to show that x hat is in the convex hull of A intersect with the convex hull of B. Okay, that's what we want to show at the end. Okay, if you can show that, then without loss of generality, the first set is contained in the second. Okay, so how do we show that? So since x hat is in the convex hull of A intersect with B, then by definition of the convex hull, there exist points, let's say x1 all the way to xn, that is in the intersection of A and B, such that x hat is a convex combination of those points, right? Maybe lambda I greater than or equal to 0, and sum of lambda I from 1 to n equals to 1. Right? So this is just a definition of a convex combination. Right? So if this x hat is in the convex hull of the intersection, there must exist some finite points in the intersection such that x hat is a convex combination of those points, right? So with that, it is almost obvious, right? Since x1 all the way to xn are in the intersection of A and B, then we know that, or maybe x1 all the way to and xn is in A, and they are in B as well. Right? Since they are in the intersection, that's just the definition of intersection. So then you can pick the same lambda value, right? And then x hat, you pick the same lambda I values as those lambda I values we defined before. You can show that x hat is a convex combination of points in A, and it is also a convex combination of the points in B, right? So this implies x hat is in the convex hull of A, and this implies x hat is in the convex hull of B, right? So therefore, with this, that implies x hat is in the convex hull of A intersect with convex hull of B, right? Okay, so that's the end of the proof, right? You just pick on any arbitrary point in the convex hull of the intersection, then you show that they must be part of the intersection of two convex hulls. Okay. Any questions here? Yes.
You don't require that we show a counterexample for the other way around?
So you are saying that you want to show that the other there exists a point in the other way that are not in the you can pick a toy example to show that.
Okay.
But here I'm just showing one direction. You can
Would you require that in the exam?
no, you just need to show one direction. Actually, I can ask you a further question. Is that when A and B are both convex sets, these two sets are equal. Okay. Yeah. But for non-convex set, you can pick a toy example that these two sets are not equal. One is strictly contained in the other. Okay. So with that, we know that the second set is more constrained, right? Then we have Z1 star is less than or equal to Z2 star. Any questions here? You don't have to take notes. I will release those notes. Okay. Yeah, so the third problem is pretty easy. You can just apply the KKT condition or the strong duality condition we talk about, right? So here you, as you can see, this problem is a bilevel optimization problem where the upper level problem is an LP in terms of U and V variables, right? And the V has to be constrained such that we minimize a linear programming problem in the lower level, right? So the lower level problem is with respect to these W variables, but V is constrained such that V has to be an optimal solution of this particular linear programming problem. Okay. So the way to do that is you will write out the optimality condition of the lower level problem, right? So this is an LP, so we can write out the optimality conditions or just refer to the lecture we had in bilevel optimization. So there are two optimality conditions you can use. We don't prefer one to another. Either you write out the KKT condition or the strong duality. Okay, so I'm not going to the details of this. You can just refer to the notes. We do have this in the notes, right? But when you write out this optimality condition, it is not an MLP, right? It has complementarity constraint. Then we show a way where you can use a big M reformulation to reformulate that into an MLP. All those are in the notes, so I will skip this problem here. You can check the notes of bilevel optimization.
Professor?
Yes?
When I was preparing that exercise, I was wondering for the big M reformulation,
Yeah.
do we need to pick up the value of?
You don't need to do that because for this, we do not give you a numerical value, right? So we don't know what the optimal big M is. Yeah.
Do we also need to say that V is greater than equal to 0 above, because we have already said that W is greater than equal to 0 in the level 2 optimization problem.
Yeah, of course. When you write down the optimality condition, that involves primal feasibility. Right? So W greater than equal to 0 is part of primal feasibility. And of course, it happens to be the same as V greater than equal to 0. Yeah. So if you can move as you said, you can remove this constraint as well. Yeah, it's okay. Yeah. Any other questions here? All right, then problem 4 is also a standard question where how do you derive generalized Bender's cut, right? So recall that actually there are some connections between Bender's cut and generalized Bender's cut. The intuition are the same. You want to derive some cutting planes to underestimate the value function of the lower level problem, right? So in the stochastic program, what we did is you want to estimate the expected cost in your second stage using some Bender's cut. Generalized Bender's is a generalization of Bender's for nonlinear problems, right? So you can write, I'm not going to solve this problem right away, but you can refer to the notes, but just to help you guys understand generalized Bender's decomposition a little bit better, you can always rewrite the problem as the following. So this is a problem involve x and y variables. We can rewrite this as d transpose y plus, let's say, a value function of y that we define later. Okay, so let's first write out the constraint on y. So y is a 0, 1 variable. Okay. So how to define Vy? So by definition, we can define Vy as the following problem, which is minimize over x, C transpose x, Ay plus g of x less than or equal to 0, and bx less than or equal to b, x greater than or equal to 0. Right? So this formulation and the original problem are equivalent. You just put all the heavy liftings within this function v of y. Right? So the idea of Bender's decomposition is you want to project the full space problem onto the space of y variables, right? So how do we do the projection? Remember that in the linear case, the way to do the projection is like you take all the extreme rays and extreme points, and then you add cutting planes to the Bender's master problem, right? But in the nonlinear case, how do you do the projection? Because the number of extreme points and extreme rays are not finite, right? Actually, we cannot define extreme points and extreme rays in nonlinear problem, right? But here, you can use the optimality conditions of these, let's call it a value function, to derive some cutting planes, right? Such that you don't need to explicitly solve for the x variable in this type of master problem. Right? So that the format of the master problem in generalized Bender's is usually, say minimize d transpose y plus alpha. So you can use alpha to represent like a value function. And then the form of the cuts is usually something like you can define a beta k transpose y plus gamma k for k from 1 to capital K. So this is a form of generalized Bender's cut you derive, and y has to be, right? So you can think about this Vy function as a very nasty function, right? You don't know the Vy function in explicit form. Actually, you can show that when the problem is, when this problem is convex, Vy should be a convex function, okay? So the intuition is like you want to add some cutting planes to approximate this Vy function, like those cutting planes, right? But since Vy doesn't have a closed form, you have to iteratively solve this optimization problem again to get those cutting planes. Right? That's the intuition of generalized Bender's decomposition. So the way to derive that, try to remember the way to derive that is that first you need to solve an NLP, right? For fixed yk, solve an NLP to get the optimal primal and dual, and combine the KKT conditions of the NLP with the outer approximation cuts, right? Essentially, if you remember what we did in the proof is that we use the optimal dual of the NLP subproblem to aggregate the outer approximation cuts. And then you derive the generalized Bender's cut. Okay. That's an intuition of doing this. Any question? Yes.
So do we have to actually derive that linear formula?
Yeah,
for
yeah.
elimination of the GX?
Right, yeah. So that's what you need to do for this problem. Okay. I just want to first show an intuition before I show the derivation. So now maybe I can show a derivation. Let's say, pause here to see if there are any questions related to the intuition here. Yes?
So the second, that is the cut we are trying to generate.
Yeah, so the form of the cut will be in this form, right? The cuts will only be with respect to the y variables. It doesn't contain any x variables here. Okay, yeah. Any other questions here? Yeah. So now let's derive this cutting plane, right? Okay. So first of all, it says you want to derive a cutting plane for y fixed at yk, right? So when y is fixed at yk, you are essentially solving the following nonlinear programming problem. Y fixed to yk, then you minimize over x, C transpose x, ayk plus gx less than or equal to 0. Right? So that's a problem we are solving once you fix y and yk. Right? So now let's suppose after we solve this nonlinear programming problem, we get the optimal primal and dual solution from this nonlinear programming problem. Right? So let's suppose the optimal primal is called xk, and then for each of these constraints, the optimal dual is lambda I k greater than or equal to 0, and this is let's say mu k greater than or equal to 0, and we have let's call it mu k greater than or equal to 0, right here. And then with that, we know that the primal and dual solution of this nonlinear programming problem, supposedly g of x is a convex function, then they must satisfy the KKT conditions, right? So the KKT condition will, how does it look like? First of all, let's just write down the stationarity condition. Hopefully, you guys now are all fluent with, writing out the KKT conditions. So they should be C plus sigma of I to, let's denote all the nonlinear constraints F from 1 to m, lambda ik, the gradient of the i's constraint, then plus mu should be mu transpose b, or should be b transpose mu. Right, and then minus vk equals to 0. That's a stationarity condition of this problem. Maybe people can double check if I did it correctly.
So the gradient of GI is evaluated at xk.
Oh, yeah, you are right, yeah. Yeah. Okay, so actually we only need a stationarity condition to derive the Bender's cut. Okay, so this is part of the KKT condition. Then the other thing we need is, let's say, the outer approximation cuts at xk. Right, so the outer approximation cuts at xk would include first of all, we have the objective, right? Alpha is greater than or equal to C transpose X. Then we have a YK plus the G of XK plus the gradient maybe let's write it out as the ith constraint here. Gi of x. Let's write this as the ith row of the linear term. And all the other linear term just follow. Okay. So those are the OA cuts you are going to write if you don't aggregate those constraints. Now remember, the way to aggregate those constraints is that you want to get rid of the x variables here, right? The way to get rid of the x variables is to aggregate those constraints, right? So actually you will multiply this constraint by 1 and multiply those constraints by lambda I k and multiply this by mu k. And this by vk, right? So after you aggregate those constraints by the optimal dual variables, and you will find out all the x term will be canceled out with the stationarity condition, right? Because the stationarity condition is the sum of something equals to 0, right? And if you multiply this stationarity condition by x minus xk, because here you have a x minus xk term, right? So this should be gi transpose. So you have a x minus xk term here. But here you have the gradient of gi of x. So you are missing a x minus xk term. You can just multiply this constraint by x minus xk. So that would be. So let's denote this as equation 1. So you can do equation 1 transpose x minus xk. Then we will get C transpose x minus xk plus I from 1 to m lambda ik, the gradient equals to 0. Okay. So now you will find out that after you do the aggregation, all the terms related to x will be canceled out by this equation. Just plug in this equation to the aggregation of OA cuts. Then you will get a generalized Bender's cut. Yes?
In the lecture, you applied the OA cuts to the MILP subproblem.
Apply the OA cuts to the MILP, right?
No, MILP.
Yeah.
You had OA x and y.
Yeah.
But here we only have.
Yeah, so the reason you don't alter approximation y here is because all the terms related to y are linear, right? Even if, let's say, if you have a linear term, ay, right? This is a linear term. What does the outer approximation cut look like? That would look like a yk times the gradient is a itself, right? That would be y minus yk. That would be just be the linear function itself, right? When you outer approximate a linear function, it's just a linear function. Right? Okay. Any other questions here?
Why did we use GIs? We have only one G, right?
Yeah, so G is you can have multiple functions, right? G can be a function of from Rn to Rn.
Okay, and
Right.
it was not given in the question, so that's why.
Oh, okay, yeah. So you yeah, maybe I should write it out as, but it is kind of given since A is a matrix here, right? If this is a single constraint, you will write this as a vector, right? Since A is a matrix, let's say A is a M by N matrix, then G should be a function from Rn to Rn, right? Just for the dimension to be consistent.
And also YK should be feasible, right?
YK
For
should be.
trying to derive a cut.
Yeah, so let's just assume YK is feasible, yeah. Right, so I'm not going to do the detailed algebra here. If you have these two things here, you almost get full points, but you should do the calculation, to aggregate those OA cuts and then use this equation to eliminate all the terms related to X. Okay. Okay, I have to speed up a little bit. So here, problem 5 is related to Lagrangian relaxation. So here, we just want to test you whether you understand the primal characterization of Lagrangian relaxation or not, right? And you can draw a 2D picture to help you visualize this problem. So let's first draw the feasible region of this problem here. Right, we only have two variables where x1 and x2 are integer variables. Right. So the first constraint is 5x1 plus 3 x2 less than or equal to 7.5. Right. So when x1 is equal to 1, let's say you can try to plot it. When x1 is equal to 0, so it's x1. Then x2 is equals to 2.5, right? So this is 2.5, and then when x2 is equals to 0, this should be 1.5. So this is essentially describing this particular line here, right? Yeah. And then we have x2 is less than or equal to 1.5 plus x1. Okay, so here, let's assume perhaps this is 1.5. And then the second line is essentially looks something like this. Okay. So what is a feasible region of this problem here? Let's consider the linear programming relaxation first. The linear programming relaxation, the feasible region of the LP relaxation is essentially this polyhedral here, right? That's a feasible region of the linear programming relaxation. So if you consider what is the question A is asking what is the optimal solution of the linear programming relaxation of this problem and this optimal objective value. So the linear programming relaxation always is obtained at an extreme point, right? And then the objective is to minimize x1 plus x2. Oh, so actually I should probably do maximize. This is too trivial if you do minimize. Yeah. So let's change this problem a little bit. We just do maximize x1 plus x2 here. And then the optimal solution, I guess it should be this point, right? You can check all the extreme points to see which one maximize x1 plus x2. I would guess it should be this point here since we have a maximization. It is probably this point, or this point. So you can check which point is larger. I guess it should be this one. And then for problem B, consider the Lagrangian relaxation where we dualize the second constraint. what is the value of the Lagrangian relaxation. So we know that when you calculate the value of the Lagrangian relaxation, it is equal to the convex hull of the constraint you did not dualize intersect with the constraint you dualize, right? So if you dualize this particular constraint here, right? So maybe draw it in different lines. If you dualize this purple constraint, then what is left is this feasible region here, and also the integrality constraint, right? So let's check what are the feasible points after you dualize this particular constraint. That will be 0, 0 is a feasible point, and then 1, 0 is a feasible point, right? And then here we have maybe this is 0, 1, and then 0, 2 is also a feasible point. Is maybe 1, 1 is also no, 1, 1 is not a feasible point, right? If you consider this constraint when x1 is equal to 1, x2 is equal to 1, then it is greater than 7.5. So all the feasible points are actually, let's see how many, 4 feasible points, integer feasible points, right? And if you consider the convex hull of the integer points that you did not dualize, that will be maybe using a different color. This region is the convex hull of the constraints you did not dualize, right? And you need to intersect with this convex hull with that constraint you did not dualize, right? So the feasible region of the primal characterization is this orange region intersect with the constraint we dualize. That will be this particular region here, right? So I cannot draw it at the same time, but this pink region will be the region of the primal characterization. Then you can calculate the value of the Lagrangian relaxation from this pink region. Okay. Yeah. So if you don't remember that, just check what we talk about is this is called primal characterization of Lagrangian relaxation. Any questions here? Okay. So 6A should be pretty easy. You can just check the lecture of bilevel optimization. Okay. And then we talk about this type of problem in robust optimization. Right? Essentially, you want to find a variable x such that in the worst case, you are still performing pretty well, right? So here the maximization problem is supposedly there is someone that acts against you. You are picking a point that is the worst case for the leader, which is x. Right? And then you can show that this can be formulated as a semi-infinite programming problem just by doing the following. So this is equal to minimize x. You can write the objective as alpha. So alpha should be greater than or equal to fx theta for all theta belongs to t. And then you write out the constraint. And x is in Rn. So this is a semi-infinite programming problem because you have a finite number of variables but an infinite number of constraints. Any questions here? And check the notes of bilevel optimization. So here it is related to the first part of the lecture, right? So in the final exam, the focus will be on the second part of the lecture, but we will also have a couple of problems related to the first part, right? So when you are reviewing for the exam, you can focus on the second part. Don't forget the basics in the first part. We will have around, let's say, around 30% of the question related to the first part, right? That's what you have done in the middle, in the midterm exam. Okay, so this is related to the first part, related to the logic propositions and how tight the linear programming relaxation is, right? So it is proposed that you can represent the logic condition using this set of constraints, right? So and it says, is this a tighter model than the following linear inequality constraints, right? So this is a general question, meaning that if I give you two MLP formulations, how do you compare these two formulations, right? So we talk about to compare the linear programming relaxation, basically what you do is that to prove that one polyhedral set is contained in the other, or vice versa, right? So how do you prove one polyhedral set is contained in the other, right? That is something called general theorem of alternative, right? It's related to the Farkas lemma and linear programming duality, right? Basically, you need to find some Lagrangian multiplier. You aggregate the constraint in polyhedral 1, and that implies a constraint in the second polyhedral, right? So if all the constraints in the second constraint sets are implied by the constraint in the first one, then that means the first constraint set is more constrained than the second one. That's the intuition here, right? Let's look at this problem here, right? Let's first write out the linear programming relaxation of formulation 1. Right? So it only has one integer variable, delta. Delta is a 0, 1 variable. So in a linear programming relaxation, you just relax delta as something between 0 and 1. Right? So the LP relaxation for the first formulation is nothing but y1 equals to 0. y2 equals to delta. And since we are talking about linear programming relaxation, we have delta is between 0 and 1, and y2 is between 0 and 1, right? So with this, clearly, you can get rid of the delta, right? Since y2 equals to delta, y2 is between 0 and 1, delta is between 0 and 1. So this is just the same thing as y1 equals to 0, and y2 is between 0 and 1, right? Okay. So if you were to plot this, let's just give you some geometric intuition. You don't have to plot this when you answer the question. You can just show it algebraically, right? So this is y1, this is y2. Basically, the feasible region of the first problem is describing this line segment between 0 and 1 here, right? So y1 can only be 0. So this is a feasible region of the first formulation. Okay, so now let's consider the LP relaxation of the second formulation. It is y1 less than equal to y2, and y1 plus y2 less than equal to 1, and they are both between 0 and 1. Right? So how does this feasible region look like? You can also draw a plot very quickly. This is y1, y2, right? So then we have y1 is less than or equal to y2. Okay, I think I may made the problem wrong. So then y1 plus y2 less than or equal to 1. are both between 0 and 1. Yeah, I should probably, yeah, I think I made a typo in the problem. This one should probably be, yeah. Should probably be the other way around. Oh no, should be correct. Yeah, so the feasible region of this problem should be this region here. Yeah, I think that this is correct. Yeah, the problem is correct. Yeah, so as you can see, the feasible region of the first formulation, not the feasible region, the LP relaxation of the first formulation is tighter than the second one. Right? So actually you can see one is tighter, but how do you show that in an algebraic way? Then you can show that since y1 equals to 0, y2 is between 0 and 1, and you can show that all those constraints in the second problem are implied by these two constraints. Right? Why that is true? Because let's just give an example, right? We want to show that all the constraints in the second formulation is implied in the first one. Okay, so let's give an example. We want to show y1 less than or equal to y2 is implied by the constraint in the first set, right? Okay. So this is a little bit trivial to show since y2 is greater than or equal to 0, y1 equals to 0, right? So you just combine these two constraints here, multiply each of these by 1, right? You aggregate y2 greater than or equal to 0, you can just multiply this by 1, multiply this constraint by 1, then you get y1 less than or equal to y2. Right. Okay, so that's why the first constraint is a result of the constraint we have in the first formulation. And similarly, you can show all those constraints are a result of these two constraints. Right, just by multiply the constraint by a weight. Right, the weights are like your Lagrangian multipliers. Okay, so that's this part. Any questions here? Yes.
Isn't like the two set of constraints actually equal?
Yeah, so the two sets of the constraints actually equal if you add the binary constraint, right? But the linear programming relaxation of the two sets of constraints are different.
Yeah, but I didn't get why we were focusing on the relaxation.
Yeah, because in solving MLP problems, you need to do some branch and bound, right? If the relaxation is tight, let's say if the relaxation is a convex hull, you don't need to do any branch and bound. You are done with the ALP. Right? So that's why in solving MLP problem, we care a lot about how tight the relaxation is. Right? So this problem is asking how do you compare the relaxation of these two formulations. Yeah. Any other questions? Here. Yeah, here the C is a naive problem. Is it possible for a nonlinear programming problem that has a convex objective function and a convex feasible region to have multiple optimum? If so, give a small example. If not, write a formal proof that the solution is always unique. Right? So here the trick is that maybe you can make up a smooth example as well. I will just make up a toy example. So if you consider a smooth function like minimize x squared, right? This is x equals to 0. For this problem, the solution is unique, right? Because the objective is strongly convex. There is only a unique solution. But we didn't say whether the convex function has to be smooth or not. You can expand this function a little bit by, let's say this is 0, this is 1, this is minus 1. Okay. So I'm kind of dividing this function into two parts. Right. On the two sides, we have the original parabola. But here you just have x equal to 0. Right. So then in this function, it has multiple minimum. Right. But it is not, I think the first order derivative is continuous. But if you look at this function, the second order derivative is not continuous. Right. The first order derivative at this constant point is, let's say, if you do consider this function as g of x, the derivative of x at this 0 point is 0, and at this point it is also 0, right? But if you consider the second order derivative of this function, the second order derivative of x squared is 2, right? But here the second order derivative is 0 at this point. So the second order derivative is not continuous, but the first order derivative is continuous for this function. Then it has multiple minimum. Okay. Any questions here? No. And D is very easy. You just replace this function by a McCormick envelope, right? So this is nothing but introduce a new variable called W is less than or equal to 8, and you write out the McCormick envelope for, I'm not going to write it out in detail, right? So for the McCormick envelope, there are 4 inequality constraints. Okay.
In the previous part, the solution would be unique for a strongly convex function, right?
Yeah, so if it's strongly convex and also it's the function is smooth, I think that should be unique. You can try proving that. If let's say if the constraints are also strongly convex, and then the function is smooth, I think you can probably prove that the solution is unique. If only the function is strongly convex, and then the constraints are just convex, I'm not so sure. I need to think about that. Perhaps we can use it as a practice exam question next semester, next year. Yeah. Okay. Any questions here?